In this video, we're going to talk about combining statements. We call them compound statements. And these combining words that we'll deal with are and, or, and not. And there's more than one word we can use to combine, like if and then. And then this expression that you might not have seen before, but if and only if. That's kind of an important one as well. And there's one more related to or called exclusive or that we'll talk about as well. So, a lot of times, instead of writing out actual statements, we'll say just something like P is some statement and Q is some other statement or something like that. So, let me give you an example with some actual statements first. So, let's say I told you that I had a coffee and I had a bagel. So let's say for breakfast, I told you these things. I had a coffee and I had a bagel. And we'll call the first bit, we'll call that P, and we'll call the second bit here Q. So let's write out a little truth table to this. What I mean by that is all possibilities for the truth values for our statements. I had a coffee and I had a bagel. So I like to do it like this. So we need the possible truth values for P, the possible truth values for Q, and the possible truth values for the compound statement P and Q. And for and, we use this little kind of wedge shape here. It's like an A without the cross. So P and Q. So, what are our possibilities? Well, maybe I did have a coffee. If I did have a coffee, well, there's two options for me having a bagel. Either I had a bagel or I didn't have a bagel. And similarly, if I didn't have coffee, either I had a bagel or I didn't have a bagel. So there are all the possible truth values that can go with these two statements. Either both P and Q are true, P is true and Q is false, P is false and Q is true, or they're both false. And of course, well, this statement here, I had a coffee and I had a bagel, is only true if both of these are true. Otherwise, I'd be lying to you. So the only time an and statement is true is when both the parts are true. So P and Q is true when both P and Q are true, and false otherwise. So that's how ands work. Or is a little bit different. We have to be careful because in English, or kind of has two meanings. In math, we have to pick one for it. So let me give you an example. Let's say I had the following, I don't know, let's say open sentences. So we'll say these will be natural numbers. And let's say I'm saying here that x is prime or x is odd. So, again, I'm going to call these P and Q, and notice the word or here. So, let's do a little truth table again. I'm going to write it a little smaller just to make myself a little more room. And for or, we have this symbol, which is like the and symbol, but upside down. It's this kind of little V. Here it is here, typed out, so it looks a little bit better. But that's how we write P or Q. And again, we have the same four scenarios. Either they're both true, only P is true, only Q is true, or they're both false. Now let's look at some examples of values from our domain that we can put in to our open sentences P and Q and determine if it's true or false. So let's say if I put in, let's say if we have something that matches, we'll go from the bottom up actually this time for something different. Let's find a situation where it's not prime and it's not odd. So something like x equals 4. So an example here is x equals 4. That's neither prime nor odd. So if I say x is prime or x is odd when x is 4, that's false. What I'm saying is false. 4 isn't prime, 4 isn't odd. So P or Q is false. Well, what about a situation where P is false, but Q is true? So we want a number that isn't prime, but is odd. So maybe something like 9. 9 isn't prime, but it is indeed odd. So if I told you that 9 is prime or 9 is odd, well, that's true. One of those is true. 9 is odd. So if I told you that, I wouldn't be lying to you. That is indeed true. What about the other situation where P is true and Q is false? So we want a prime number that isn't odd. So that would be, in fact, there's only one of them, of course, because odd means not divisible by 2. So the only prime that is divisible by 2, by definition of what a prime is 2. That's a number that is prime and not odd. So if I said 2 is prime or 2 is odd, well, that's a true statement because, well, 2 is prime. So here we have when just P is true, then P or Q is true. And finally, if we have a situation where both are true, maybe a number like, well, 3. 3 is a prime number. 3 is odd. So here an example would be x equals 3. What happens here? So if I told you, well, 3 is prime or 3 is odd, well, here they're both true. And we have to make a little choice because in a lot of situations we want or to be true when both are true, or we want or to be true when exactly one is true. And in math, we found it a little bit easier to say, well, we'll make or true when both P and Q are true. So with or, it's related to and, of course, but it's kind of it's opposite in a way. So and was only true when both P and Q were true. Or is only false when P and Q are false. Another word it's not so much a combining word, but it's an important word. It's this not word. And basically, that just changes when an expression is true or false. So if we had an expression P, then not P, which we usually write with a little tilde before it, so it means the negation of P. When P is true, of course, the negation is false. And when P is false, the negation is, of course, true. That one's kind of pretty self-evident. Let me give you a couple of examples. So, if P was the following, I love coffee. Well, the negation, be careful here. It wouldn't be I hate coffee, because maybe I like coffee, but I don't love it. So if I love coffee is false, it's just I don't love coffee. So keep that in mind, that when I'm negating something, it has to cover all my possible bases. So if I love coffee is false, then I don't love coffee has to be true, which means anything besides love. Let me give you one more example. So this one will be an open sentence. So let's say that my variable is going to be, let's go with the natural numbers. And let's say the statement Q, I'll use a different letter. Let's say Q is X is greater than or equal to 4. Okay, so let's write down, remember this is an open sentence, so it's going to be true for some values and false for some others. Well, it's false if X equals 1, 2, or 3. Remember, counting numbers are 1, 2, 3, 4, 5, all the way to infinity. So this is false when X is 1, 2, or 3. And if it's 4 or bigger, then it's true. So it's true otherwise. Okay, what I want you to do, pause the video now and see if you can write the expression for the negation of Q. Remember, we wanted to have the opposite truth values. So it needs to be true when the original statement is false, and false when the original statement is true. So pause the video now and try that. Okay, so now that you're back, well, we need a statement that is true when X equals 1, 2, or 3, and false otherwise. That's what we need. So we need that it's true for X equals 1, 2, and 3, and false otherwise. So I will first write down a mistake that lots of people make. They'll see just the greater than or equals to, so they'll just change it to the less than or equals to. They'll say, all right, less than or equals to 4. But the problem with that is 4. Well, 4 made this statement here true in Q. So not Q, we need it to be false. But if we put 4 into this expression here, it's still true. So it didn't get negated when X equals 4. So that's no good. We want just less than. So X is less than 4 will work, because this is true when X equals 1, 2, or 3, and false for any other natural number or any other counting number. 4 is not less than 4. 5 is definitely not less than 4, and anything bigger is not less than 4. So this works. Or you could write it another way if you wanted to write it as X is less than or equal to 3. That would work as well. Remember, in a lot of scenarios, you can write statements in different ways. The next one is this XOR. The way we read it really is exclusive OR. And that's kind of that other case of OR, where we don't want it to be true when both are true. So it's probably easier just to write the truth table for this. So again, it involves two statements, and we need this P exclusive OR Q, and the symbol for exclusive OR is a circle plus, and we'll do each of the possibilities for P and Q in terms of their truth values. And so exclusive OR is only true when exactly one of P and Q are true, and it's false when either both are true or both are false. So even more than what we've been doing, we can combine these combined statements as well. So we're going to do an example here. I'm going to do a few examples. So I have 4 statements here. We are in Winnipeg is the first. 1 plus 1 doesn't equal 2 is the second. All cats are gray is the third. Some cats are gray is the fourth. So let's write the truth values of these down. We are in Winnipeg. I'm going to say this is true. I wrote these notes like we would be in class, and so we are in Winnipeg would be true if we were in class. Let's just say it's true. 1 plus 1 doesn't equal 2. That is false, of course, since it does equal 2. All cats are gray. Well, I can show you a cat that isn't gray. I think most people can think of a cat that isn't gray. Garfield, for example. So all cats are gray is false. And some cats are gray. There are gray cats out there. So that is true. Okay. So let me write down a statement combining these. And it's going to be a little bit complicated. Let's do P and Q or not R. So let's figure this out. Let's do a little bit of a truth table. We really only need one row since we know the truth values of these statements. But we have a P, a Q, and I'll put R, and I'll put S too because we can use that later. And we know that P is true. We know Q is false. We know R is false. And we know S is true. So we can kind of just figure out truth values based on this. I don't need that much room, actually. Just by kind of breaking down our statements here into little chunks. So what we're going to do, we need not R. We need the negation of R. So let's figure that out next. So the negation of R. So R is false. So the negation of R is true. Now we can do Q or the negation of R. So let's do that. Q or the negation of R. That's this bit here. So we have Q or the negation of R. We know Q is false, but the negation of R is true. At least one of them has to be true for an or statement to be true. So this is true since not R is true. Well, let me do that in black, actually. Sorry. And then finally, we have kind of everything put together. We have P and Q or the negation of R. So here we have an and with two parts. We have the P part, and then we have the Q or the negation of R part. So let's look at the truth value of each one of those. So P is true. Q or the negation of R is true. And remember, ands are true exactly when both parts are true. So this is indeed a true statement. And that's how to do kind of all of these. You just kind of break it down into its constituents and you keep going. Let's do two more. Let's do the negation of P exclusive or Q or S and the negation of R. Okay. So I'm going to erase this and just write it again to give myself a little more room. But we're just going to do the same thing. So we need a P, we need a Q, we need an R, we need an S, and we know this is true, false, false, true. And maybe it's a good idea here if you pause the video and you try this one yourself. See if you can do this one. If you can do this one, you're on the right track. So pause the video and give it a go. Okay, let's get to it. So you might have approached it slightly differently than me, but probably not that differently. So let's figure out what the brackets are first. So we need P exclusive or Q Okay. So what do we have here? We have P is true and Q is false. Exclusive OR, we need exactly one to be true. So this is indeed true. Excellent. Now let's do S and the negation of R. We need to figure out what the negation of R is. R is false, so the negation is true. So S and the negation of R. Well, S is true. The negation of R is true. So S and the negation of R is true, just like before. Both S and the negation were true, so that means that the combination and statement is true. And we need the negation of that. So we need the negation of... Or sorry, we don't need the negation of that. My mistake. We need the negation of P exclusive OR Q. Well, P exclusive OR Q was true, so the negation is, of course, false. And then finally, just in the interest of room, I'm going to call this expression S and the negation of R. I'm going to call that X. And I'm going to call, oh, these, sorry, it should be colon equals there since I'm naming this thing X. And I'll call this guy Y. I'll put the colon next to the Y. Okay. So the last one, everything put together, Y or X. Well, what's that going to be? Well, Y is false, X is true. So Y or X, well, we only need one of those to be true for the OR to be true. So this is indeed true. All right. And the last one, in fact, is very, very similar to the one we just did. I will leave that as an exercise for you guys. I will tell you that the last one here, you can do it as an exercise. You should get that this compound statement is indeed true. So let's get down to a couple of points here. So when we're writing things out in terms of these variables, say we name the statement we are in Winnipeg P, like we did up here. When we write statements like that using kind of these logical symbols, we call it a logical formula for the assertion. So these here that we're writing down are logical formulas. And as a little example, we can try to express this statement, 51 is a prime, or pi equals 3.14, as a logical formula, and then determine its truth value. In fact, it's a little bit easier than what we've been doing up here. So maybe pause the video now, try that, give it a go. Okay, now that we're back, well, if we want to write this as a logical formula, it's a good idea to name these statements. I've been using P, Q, R, and S before. Let's change it up just for fun. Let's call it, I don't know, A and B. Let's say A is the statement 51 is a prime. And let's say B is the statement pi equals 3.14. Well, let's determine the truth values of these statements. They're statements, so they have truth values. Is 51 prime? Well, I will tell you that 3 times 17 is 51. So I wrote 51 as a multiplication of two numbers that are not one in itself. So it's not prime. So 51 is a prime is a false statement. And from the previous slide, we know that pi doesn't equal 3.14. So the logical formula is A, and there's an OR here, so it's going to be A or B. That's our logical formula for this assertion here. And that is, of course, well, we know that A is false, we know that B is false, and an OR is false when both are false. So this is a false logical formula. In subsequent videos, we're going to be a little more precise with these things. We're going to work on order of operations of these logical symbols, just so we have a way of doing them. If we have a string of them kind of put together, we need some sort of agreement so that everybody knows which ones to do first. I will say it's a common practice in some sense to use brackets liberally, so it's really, really obvious what you do first and what goes together. So when you are doing these and you're writing out logical formulas, if they're quite complex, don't be afraid to use brackets to write what you want.